leave it behind.
How'd you love them stoics?
Well, what I had to grade on the tests were pretty doggone good, but there's still a lot of people that still have to take that because of the testing and all that good stuff.
These stoics, what?
Is this the last chapter?
Well, no. We're going to cover a little bit of 8 and then go back and do just a little bit of 6. This is actually something we always wish that we could get in before you take the ACTs. It's conics. And conics always show up on entrance exams when you take them for college. Lots of you probably already took your entrance exams. How many people already had to do the math entrance exam online? Nobody? Okay, so you're in the process, yeah. Because there are several colleges that will let you do that online. And you definitely want to pass that. Because if you don't, what happens is you have to pay for remedial courses in math that don't apply for your graduation. So you can pay up to probably $800 for a remedial course, and it won't even show up on your transcript going towards your graduation because it's a remedial course. So conics are a huge deal on them. So Oval Lawn at the White House, and it is called the Ellipse because that's what it is. Has views of just about everything you could want to see in Washington, D.C., Washington Monument, etc. But this says the ellipse is 616 feet long, while only 528 feet wide in the shape of the conic section. And in the White House, there is a room that is shaped like an ellipse. And the cool thing about it is, before anybody really knew what was going on, there are 2 spots in an elliptical room where if you stand at those spots, you can hear people whispering in the room. You can hear what they're saying. And it's called the whispering room. And yeah, they used it to spy on people way back in the day. But now people know about it, so it kind of defeats the purpose. Everybody knows to stay away from that room. So our overview here is analytic geometry is what we're doing. Anybody see the movie? I was just thinking about this morning. Hidden Figures. And anybody go see it? Very cool. And they talk about how they need somebody that knows analytic geometry because, of course, when you're studying things in space, you want to go into orbit and come back down, and you need to know how all of that math works to make everything that we do, the space shuttles and all that good stuff work. So analytic geometry combines number and form, grew from the work of Frenchman René Descartes, the Cartesian coordinate plane guy. He did a lot of math. And Pierre de Fermat, which he also did some stuff in calculus. Their achievements allowed geometry problems to be solved algebraically and algebra problems to be solved geometrically, putting those 2 things together. So analytic geometry opened the door for Newton and Leibniz to develop calculus. So, like I said, Fermat is often thanked for his introductions into the study of calculus. And like it says, you already had some experience with circles. We just reviewed briefly circles in the last chapter. And now we're going to talk about the other conic sections, the parabolas, ellipses, hyperbolas, and how those are expressed as second-degree equations, so x-squared equations. Conic sections are the paths of nature. Scoot that up. Gosh, you can't see it in the packet except that front page is dark. So conic sections are the paths of nature. Any free-moving object in a gravitational field allows the path of a conic section. Therefore, we'll investigate their uses, including reflective properties of parabolas and ellipses, and how hyperbolas are used in long-range navigation. A dish. Many people have a dish sitting on their house somewhere that's supposed to capture all those television signals. And they are in a parabolic shape. So why do they do that? That's part of what we want to study here is how do you get this stuff to work. And then over here, just a little more history, where it talks about parabolas, ellipses, and hyperbolas. They had been around. They've been around for a long time. Apollonius had those, and he wrote an 8-volume book called Conic Sections. But they didn't really have the algebraic capabilities back then to do the things that we did. So down here, it talks about how Galileo kind of brought that all together and said, we really need this because we're studying the stars, and we need this information. So they went forward from there. And then, of course, discovered planets and travel and using elliptical orbits to go through. So the space system definitely uses our conic sections. Yeah, you too. And See Hidden Figures. Great movie because it talks about math, but it also has a lot of really good lessons behind it. So what we want to be able to do, our objectives in 8.1 are understand how conic sections are formed, understand the geometry of parabolas and their key features. We might even get a little bit into writing equations for parabolas today. Translate parabolas, right, left, up, and down, and understand applications of parabolas. Now that's word problems. That's probably end of day 2, beginning of day 3 when we get there. So that won't be today. But conic sections come from what is called a double mapped cone. And it really is, if you just took a snow cone holder and turned another one upside down on top of it, that's a double mapped cone. And it's all the shapes that can happen if you slice that double mapped cone and then open up what you have. Those are the shapes that are called conic sections. So imagine two non-perpendicular lines intersecting at point B, right here. And then if we fix one of the lines on the as an axis and rotate the other line, the generator, we'll form this right circular cone, the vertex V. Notice that V divides the cone into 2 parts, naps, called the double napped cone, with each nap of the cone resembling a pointed ice cream cone. Bless you. So, we start cutting away on that. And when we start making those slices through there, what we're trying to do is see what shapes are formed. So that's going to be a conic section or conic. It's a cross section of the cone. The intersection of a plane with a right circular cone. Way back in geometry, we have you try to visualize these. So when your teacher would give you a cube, and then they'd show you, hey, if we sliced right here and opened it up, what would the figure be that would be achieved by this? So for a cube, you could get a triangle if you cut off the very corner of a cube. Those types of things are what we're talking about, those conic sections. The 3 basics: parabolas, ellipses, and hyperbolas. Hyperbolas have at least 2 branches. So you can kind of imagine, cutting through this cone so that you can end up with 2 branches off of it. By kind of cutting out vertically. If you just took a knife and chopped it down vertically, you could see these 2 pieces coming out, and that would be the hyperbolas that we have there. But we're going to study parabolas first, which would just be one of these. That's what a parabola is. It's a conic section. So, some atypical conics, known as, let's think this is funny, degenerate conic sections. They're the conic sections that walk around in the leather jackets, beating up the other conic sections. They're degenerates. Are shown below because it is atypical, lacks a lot of the features that we usually will use for an ellipse, a circle, and those are degenerate ellipses. Other degenerate conic sections can be obtained from other conic section cutouts that we have here. Cones occur when the generator and the axis of the cone are parallel or perpendicular, and we have the 3 nice ones up on the top. The 3 nice ones that we're going to study. Oh, you know what? Could I ask you, are you going to be hanging out in the office eventually? All right, so we can get an ellipse, a parabola, and a hyperbola. Those are the nice ones, but down here, these are the degenerates, the weird ones. Now, if you cut it so that you're parallel to the double mapped cone bases, you could get just 1 point. That's silly. You could also get a line. Well, we already studied lines. We know how to deal with lines if you put it in just the right spot. And then here, you could get a couple of intersecting lines, which you've already studied intersecting lines as well. So those are the degenerates. We're not going to spend any time on those. But they're another nice one. So the conic sections can be defined algebraically as the graphs of a second-degree quadratic equation in 2 variables, where a, b, and c are not all 0. Yeah, this is kind of scary. Know that we'll get here, but like not today. Yeah. So here's what we need to do. We need to figure out what the standard form equations are for each of these, and then we're going to make All right. So we'll start with parabolas. Because you've already done parabolas before. Like I said, you studied parabolas that open up and down. So what makes that open up and down? The x squared. So today what we're going to do is we're going to say, okay, that was up and down. I really need parabolas that open right and left. How do I do that? You do this. You square the y instead. So that basic, it's not exactly everything we need to know about it. Obviously, we'll see that in a minute here. But that is really the key to remembering, okay, which one does what? Oh yeah, we used to be able to graph these on our calculator because we always had y equals and it was x squared. And then with these, this is the new one. You know, instead of squaring the x, I'm going to square the y. And that'll give me my left and right opening. But there's more to it than that. These are the parent functions because there isn't more to them than that. You know, it's just y equals x squared. There's no number sitting in there. If you want a number, you put a 1 in. That's what you do. That's y equals 1x squared. So away we go. Going to get a little more in depth than that. Geometry of a parabola. A parabola is a set of all points in a plane equidistant from a particular line. That line is called the directrix. The directrix is a line that tells us, don't draw the parabola this way, go the other way. It gives directions. That's what a directrix does. Don't go this way, go the other way. Because what it's going to wrap around is called the focus. And so the directrix sits behind and says, the focus is over there. Go that way instead. So it gives us those directions. The line passing through the focus and perpendicular to the directrix is the focal axis of the parabola. I was just thinking you really need the visual for this. This is the focal axis right here. It's perpendicular to the directrix, but it goes right through that vertex and that focus. And that's obviously important when we're talking about how this thing is formed. So it says the axis is the line of symmetry for the parabola. Notice we're not just doing up and down anymore. We're having a little turn on this one, a little bit of a rotation. The point where the parabola intersects its axis is the vertex. Talked about that at any time you were graphing parabolas. In fact, we would complete the square in algebra 2 to try to put things in vertex form. The vertex is located midway between the focus and the directrix. That's huge. I always think we should maybe like capitalize that. So this vertex right here, the distance from the vertex to the focus is exactly the same as the distance from the vertex to the directrix. Those will always be the same. And it's the point of the parabola that is closest to both the focus and the directrix. So how does it get its shape? It gets its shape because if you pick a point on the parabola anywhere, it has to have exactly the same distance to the directrix as it does to the focus. That's what makes a parabola. So you can put 2 hash marks right there to show that that is always the case. That's what makes it wrap around. And it says up there, the distance from each point on the parabola to both the focus and the directrix is the same. That's what forms it. That's why a parabola looks the way that it does. So we've got a lot to do here. Because obviously there's numbers involved in making something like this happen. So, pretty important numbers. How far is it from here to here? The vertex to the focus. That's going to be a really important number for us. When we're graphing, we sure would like to know, how wide is this thing? That's another thing we're going to be able to know by the time we get done with it. So let's put our visual together with what we're going to do. Standard form for a parabola. Again, this one you've studied before. Upward or downward opening is x squared equals. Now notice it's not just 1 in front of the y this time. We've got 4py. Okay, so what's p? is the distance from the vertex to the focus, or the distance from the vertex to the directrix, because they're both the same. But this book will call it the directed distance. And that's because if we find a p-value and it's negative, we should know that that's telling us it's going to go left or down. If we find a p-value that's positive, it's telling us we should know it opens to the right or up. So, like I said, it's important that we find that little piece of information. Now notice, this one says if p is greater than 0, we're opening up. If p is less than 0, we're opening down. So positive and negative make perfect sense here. Positive for up, negative for down. And we see a lot of the same things that were on that last drawing. We're seeing the distance p that's the same here, and then the distance from the focus point on the parabola will be the same as the distance from the spot on the parabola to the directrix. I know it's not to scale, it doesn't look that way, but it's supposed to be. And then, like I said, very important that you know the vertex lies halfway between the directrix and the focus. So if they give us a parabola, then what we want to do is use that information to say, okay, where's that vertex at? How can I find that information? And this is just going to be an upside down drawing of the same thing. Difference between this one and the one up top, now it's y squared. And this one's going right or left. And if p is greater than 0, it makes sense it should go to the right. And if p is less than 0, it makes sense it's going to the left. And with this one, you can definitely see the directrix back here saying, don't put the parabola this way, draw it that way. Here's my directrix. Go the other way, wrap yourself around the focus. That's what you're supposed to do. So it uses the same concepts. It's a matter of us knowing it's x squared. That's up and down. Well, that was y squared. That's going to be right and left. And using that information. So, away we go. Vocab like crazy for these things, but we use a lot of it in multiple ways. So, blue b is the focal length. How long is it from the focus to the vertex? Now, like I said, this book is going to call this the directed distance, because if it's negative, that should tell us it needs to go left or down, one of those two. Then, a chord. What about this in geometry? A chord is a line segment that has endpoints on a parabola. We're going to talk about a specific chord that goes through the focus of a parabola, and actually going to be perpendicular to the axis, focal axis. This little absolute value of 4p values here, that's because this is really a length or a distance, and that's called a focal width. That tells us how wide the parabola is at the focus. And that's going to be a big time saver when we go graph. So the length of the chord through the focus is perpendicular to its axis. So this little box here summarizes everything. And if you're a memorizer of formulas, that would be the way to go. But this is truly visual. It really is. Once you start putting things down on a grid, and you'll see, oh yeah, this one's going right, this one's going left, up, down, and you'll be able to get a feel for where all of this information goes. So something to come back to later on and make sure that it makes sense. And here's what we're going to do. It says finding the focus, directrix, and focal width of this little parabola. Find the focus, the directrix, and the focal width of y equals negative 1/3 x squared. All right. So if we go back up here and look at these formulas, we see that the formulas are built to have the x squared or the y squared by itself. Well, that's not taking place here. So I'm going to multiply both sides by negative 3. And get negative 3y equals x squared. Now I look at it and think, okay, x squared, those are up or down. This has a negative. It's going to go down. So make it a little sketch in my head. Well, it's definitely going to go through 0, 0. I mean, that's kind of a given here with the numbers we have, no matter whether you look at this one or at the original. So I know it's going to do something like that. I don't know exactly what's like that, but I do know it's going to do something like that. So it says find the focus, the directrix, and the focal length. Well, the first part is, do you know where the vertex is? And because 0, 0 is the vertex, we're starting with basics. We really are. We're not going to have an H and a K or anything else. Our vertex is going to be 0, 0. Next up would be to say, all right, this is that focal width they were talking about before. So 4p equals negative 3. Okay. Well, what that tells me is this is opening down, and the focus right here, if I measure the length of the chord that goes through that focus and is perpendicular to the axis of symmetry, this is going to be 3 units right there. Well, that's helpful with graphing, but they don't necessarily want us to graph this one. So the next thing I do is think, okay, well, I need p because p is the distance. It's the distance from the vertex to the focus and from the focus to the directrix. So if 4p equals negative 3, p is negative 3/4. Okay, so this is the axis of symmetry, and the focus is negative 3/4 down. Well, that would make that 0 and negative 3/4. And then the directrix is the line behind it saying, don't go this way, go the other way. So there's my directrix up there, and that's going to be a y equals line. And because this distance from 0 to negative 3/4 is the same as this distance, it's going to be y equals 3/4. I suppose I should go back and label my focal width. Put it on the drawing and label it. There it is. Focus, directrix, focal width. We have them. So they don't want us to necessarily graph it at this point. We're just picking out all the good stuff. Now we're supposed to write an equation. Find an equation of a parabola. Find an equation in standard form for the parabola whose directrix is the line x equals 2. Very visual. Let's draw that x equals 2 line. Now directrix are helper lines, so they really should be dashed. I wanted to make sure you could see it really well on that last one. There it is. Focus is the point negative 2, 0. Halfway between the focus and the directrix is the vertex. So where's the vertex? That's fantastic news. And then we need to know which way it opens, because we need to know if we should be using an x squared or a y squared in this thing. How do you know it opens left? Directrix is saying, don't go this way, go the other way. So it's going left. So instead of grabbing the equation y squared equals 4px, I'm going to put a negative on there right away. I don't want to forget that this one went to the left. I want that negative piece in there. All right. So because we don't have an h and a k, we don't have anything behind our x and our y. And it looks like all we have to do is figure out what p is. That's just the distance from the vertex to the focus. How far is it? 2 units. Done. That's it. Now, obviously, we're going to have to graph these eventually and all, and I want you to know the good stuff about it. So let's graph this. We're going to graph it super quick by doing this. by looking at the fact that if 4p is 8, remember absolute value of our negative 8 there would be 8. That's telling us, right now we know this. That's telling us that right here, perpendicular to this axis, if we go up 4 and down 4, we have a couple of really nice points on our parabola. I go over here, 1, 2, 3, 4, 1, 2, 3, 4. And there is my parabola. Now, if we want to be even more careful about graphing this, at this point we'd say, you know what, we always solve for y if we have to make a little table. So y equals plus or minus the square root of negative 8x. We could put in a couple of numbers if we wanted to. You know what? Especially if they just say sketch the graph. That's perfect. We've got the vertex. We know where the focus is. We have the directrix, and we know the focal width. It's great. It works. So it's a faster way to graph than you did back at exponential or in algebra 2. We don't have to make as many tables. All right. Hope for more of those. Find the focus, directrix, and focal width of this parabola. Y squared equals 12x. Let's start here. What's its vertex? It is 0, 0. We don't see any numbers behind our x's and y's, so there it is. Which way does it open? Question or yes? Go to the right. Now, how are we going to use that 12? How does that help us? And you said it open right. Well, that's going to put the focus right there. What are the coordinates for that focus? 0. Bless you. Okay, do you know that? Do you know where the directrix is? Where is it? X equals negative 3. Equal but opposite behind it, saying don't go this way. Find the focus, directrix, and focal width. Oops, we didn't do focal width yet. Which would be the next step. We did this in the right order. What would the focal width be? Right now you'd be thinking, okay, I think I know what it is, but that's way too easy. 12. It's the absolute value of 4p. Well, let's finish this up with a little graph up there. Because that would bother me to do that. What's that focal width mean? 6 up, 6 down, and we've got ourselves a parabola. We do. There it is. Again, you know, if it's on a test, definitely I would take the square root of both sides. A few more numbers in there to make sure that I'm accurately reflecting what's happening as you go out past 5, 6, 7, 8, 9, 10, those type of things. But how nice is that to have that focal width and know what it is and just be able to graph a parabola just like that. That's such a big help. All right, so we've got our sketch right there. So now, oh my goodness, that moved. Well, that's got me worried. 43210 me on what we did. I go too fast? 43210 me. How do you feel about parabolas? Okay. So let's just find, even if it's just in the margin somewhere, find a spot. Because I must have just ripped through it. Give me all the good stuff. Vertex.
0, 0.
Which way does it open? How do you know? X is squared and it's negative. So the next thing I'm going to want is the focus. How are you going to find it? So where's it at? Give me coordinates. It's easy to get turned around with the right, left, up, and down. Where's your directions? Focal width. Remember, we use absolute value because it's width, it's the distance. So what do I do with that? 12 left and better? Question? We okay? Got it? Yes. What's up? No, right here. I didn't label it focal width. I better label that. Focal width. Yeah, that was really bad. Two C's in focal. Come on. There we go. Focal width. So the 24, we split it in two. Say 12 this way, 12 that way. All right. Let's try it again. Saw some low numbers I didn't like. 4, 3, 2, 1, 0. Yeah, we've got to do another one. I want to see this locked in a little bit better. All right. A little better. Well, hey, that's a good place to stop, right? I mean, everybody's feeling like, yeah, I can do this. I can make growth on this. So before we do any H or K's, let's get this puppy down. Huh? And I remember this assignment going super fast. If you have graph paper, I better give you graph paper.
I'm just gonna do long graph paper.
Let me make sure
Yeah.
that you need it. If you don't need it today, you're gonna need it.
Yeah. Yes, I really need it.
We can't walk in halfway through their
There's 5,
fabric.
20 are gonna do it. Find the vertex. Find it.
Oh.
So I'll just write it in March.
Okay, you only need to graph 2 of them. So I'm gonna give you graph paper anyway because we're gonna need it for the next few days. But if you want to just put your graphs on normal paper, you should do that. Yes. But you definitely can graph it on as well because it'll go super fast.
Okay.
It was probably October of your algebra 2 year was the last time you graphed parabolas.
I don't know if Ashley's saying it, but I know Madison and